Hi, welcome to this video. Now in this video, we're gonna do chemical equilibrium, okay? So this is a nice topic. This is a very nice topic here in physical chemistry. So now, chemical equilibrium. So now we have classification of different types of chemical reactions. Now, if we have a look, when we have a look at this chemical reaction, we can see that we have the interaction of our reactants to form our product, in this case, which is C. So when A and B interact with one another to form C, this type of reaction, we say it is a unidirectional reaction, okay, whereby reactants form the products. And then another class of chemical reactions is what we see over here, whereby we have the reactants, which is A and B, interact with one another to form C. But you can see that C will decompose back to form the reactants because this equation, it is reversible. So now this type of equation, it is non-unidirectional reaction. Why? Because it is reversible and the products can interact with one another to form the reactants, or the products can decompose to form the reactants. So these are two classes of chemical reactions that we can actually talk about. But here in chemical equilibrium, we're only going to focus on the reversible reactions, which are non-unidirectional reactions. Now, the most important thing that we need to know about the reversible reaction is that the rate of the forward reaction, when is equals to the rate of the reverse reaction, we call that a dynamic equilibrium, okay? So when we talk about the dynamic equilibrium, it is whereby we're saying the rate of, look, this is the forward direction, right? When A plus B forms C. But remember, this reaction, it is reversible. So if I want to decompose C to form A and B, again, this is the reversible reaction. So that means in this case, this simply means that the rate of this reaction, it is going to be the same as the rate of this reaction. So when the rates are the same, we are talking about a dynamic equilibrium, okay, of the forward reaction and the reverse reaction. Now, what we see over here, it is a reversible reaction of reactants forming the products forming the reactants back. So when it is at equilibrium, and therefore we have the homogeneous equilibria. In this case, in homogeneous equilibria, it is whereby all of our substances are in the same state of matter. We can see that the reactants are in gaseous state and the products are also in gaseous state. So homo means the same. So homogeneous equilibria means that our substances in our chemical reaction are in the same on the same state of matter. Now heterogeneous mixture, hetero means different. So now heterogeneous mixture, it is most definitely going to be different from that one, whereby all of our substances maybe are presented in different matters, or one or two of them are presented in different states of matter. We can see that A is in solid, B it is in gaseous state, C gas, D in solid, for a fact that the states are not the same through the entire chemical reaction. Therefore, we are talking about a heterogeneous mixture, okay? All right, I hope that was clear. Now, we have what you call equilibrium constant. So now, when you talk about the equilibrium constant, this is what we are talking about. We have the reversible reaction, right? Whereby reactant A and B interact with one another to form product C and D. Same applies, C and D will interact with one another to form the reactants A and B. This is a reversible reaction. So we have what you call the equilibrium constant expression. What you see over here, it is what you call the equilibrium constant, okay? So now this equilibrium constant expression, we use it to determine equilibrium constant. So what we mean when you talk about the equilibrium constant, when the reaction reaches a dynamic equilibrium, we want to know the constant at which this reaction has reached its equilibrium in that case, okay? Because you know that the reactants, they're going to interact with one another and the products are going to start to be formed. As the reactants are being used up, the products are being made out of the reaction. So there is a point whereby equilibrium it is going to be reached in this chemical reaction, and therefore we would want to determine the Kc, the equilibrium constant of that reaction. We use this expression. So this expression, it is actually denoted by this formula, okay? But I'm gonna show you something. Let me show you something. Kc is equals to concentration of the products divided by molar concentration of the reactants. Molar concentration of the products divided by molar concentration of the reactants. But this, it is not the way on how we express the equilibrium constant. This will just only, or this will actually help you or to guide you how to redo this equilibrium constant in exam or wherever you are. You're not supposed to do this. This is just for a reminder that on top we have the concentrations of the products, and at the bottom we have the concentration of the reactants. You can see even on this Kc expression, we can see that at the equilibrium expression, we have A, B as our reactants, they are at the bottom, and then we have C and D in this expression, and they are at the top. So that means we are talking about the concentration of the products at the top, and we are talking about the concentration of the reactants at the bottom. And then again, when we write this Kc value, each and every time, make sure that your chemical equation, it is actually balanced, okay? So we have small letter A, B, C, and D. So these small letters, they actually represent the coefficients of our substances. We can also refer to them as molar coefficients. So now, these coefficients, like I said, make sure that your chemical equation, it is always balanced. So these coefficients, we raise them as our exponents into our equilibrium constant expression all the times, okay? So A, B, C, D, this, we call them the molar concentration. And again, pay attention to the notation. Concentration, we use square brackets, okay? Or square parentheses. We don't use round brackets. We use square brackets to denote concentration. So Kc meaning equilibrium constant using concentration. And then A and B and A, B, C, and D are coefficients. Like I said, make sure that your chemical equation, it is always balanced. And therefore, here's the most important part that I want us to discuss or talk about. When you perform your calculation based on this expression of equilibrium, say that you get that your Kc, it is less than 1, okay? Let me show you something. This is what I want to talk about. When your Kc value, it is less than 1, your equilibrium favors the forward reaction. The products dominates equilibrium. But let me break this down so that you can understand what does this actually mean. So remember, I said to you, when you want to determine the Kc, you use the concentration of the products over the concentration of the reactants all the times. Now, in this case, let's say we have high concentration of the products compared to the concentration of the reactants. That means you're going to have low compared to this one, low concentration of the reactants. Let's say, for an example, I'm going to choose any value of products, of concentration of products. Okay, let's say I have 2. Okay, sorry, I have 4. So if 4 indicates high concentration of the products, value that will indicate low concentration of the reactants supposed to be less than 4, most definitely, right? So maybe let's just pick 2 for an example. And then when you go to our AC expression to substitute our concentrations, to determine the Kc based on this information, whereby we have high concentration of the products compared to the reactants. Remember here it's 2, right? We're going to substitute over there. We're going to substitute 4 divided by reactants. It's going to be 2. And therefore, what is 2 divided by 4? It is most definitely 2. So this value, it is less than, it is greater than 1. For a fact that this value is greater than 1. Why is this value greater than 1? It's because we have a high concentration of the products over the reactants. So remember, according to chemical reaction, the products, let's say this is the forward reaction, the products are on this side of the equation. We're going to say the equilibrium will shift to the right because we have high concentration of the products since, well, our Kc value, it is greater than 1. So that means equilibrium will shift to the right. Or we can say equilibrium will favor the forward reaction. We can see that the forward reaction, it is directed to the right. And therefore, we can say the products dominate on equilibria, okay, when the Kc, it is greater than 1. But now, let's say now we want to determine whereby Kc, it is actually less than 1. Now, we have the concentration of the products, we have the concentration of the reactants once more again. Now, in this case, let's say now we have low concentration of the products, but we have high concentration of the reactants. Let's choose any number again. Okay, let's say maybe I choose 2 on this side. Obvious, if I choose 2 to be concentration of the products, reactants has high concentration. So that means reactants supposed to be greater than 2 because it has high concentration over the products. Let's say maybe I choose which is higher than 2. I choose 4 once more again. I choose 4 once more again. Now, let us determine the Kc. Remember, concentration of the products divided by the concentration of the reactants. So the concentration of the products in this case is going to be 2. And what's the concentration of the reactants? Concentration of the reactants in this case is going to be 4. Therefore, 2 divided by 4, it's how much? It is 1/2, which is 0.5. Now, this is the Kc based on this information over here. This Kc, which is 0.5, it is most definitely less than 1. Now, why is this the case, whereby the Kc is less than 1? Now, remember, when Kc is less than 1, equilibrium favors the reverse reaction. Again, let's go to this reaction. This is the forward reaction, and this is the reverse reaction. And the reverse reaction, it is the formation of the reactants, right? And then the reverse reaction, it is directed to the left. So in this case, if we get our Kc value to be 0.5, which is less than 1, that means it's because we have high concentration of the reactants over the concentration of the products. So that means equilibrium will shift to the left based on this equation. Equilibrium will shift to the left, okay? Or the reverse reaction will be favored, whereby the reactants dominate equilibrium because we have high concentration of the reactants. So each and every time your equilibrium will shift to the side with high concentration. If the products have high concentration over the reactants, say reactants have low concentration and the products have high concentration, equilibrium will always shift to the higher side. So that means in this case, equilibrium will shift to the right or will shift forward or will be favored forward. But if maybe the reactants are higher than the products, therefore, remember, equilibrium will always shift to the higher side, whereby we have high concentration of the reactants. Basically, this is how this works, but you will see when we do Le Chatelier's principle as we continue with the lesson, okay? All right. So now, again, when writing your Kc expression, which is what we see over here, always make sure that your equation, you check your equation whether it is homogeneous or it is heterogeneous. That's the first thing that you check before you write your Kc value. So on this expression, on this Kc expression, we only calculate this, we only use this formula for substances that are in this state of matter. We use gases only or aqueous species only. It's either we use gases or aqueous species only. But if your species are in liquid or are in solid, therefore you're not going to include them on the Kc expression. Now you will see when we want to determine the concentration of the liquids and solid, we're going to use density over molar mass, but you'll see as time goes by, not now. So now again, it is not always the case whereby we determine the equilibrium constant using concentration, okay? We can also use pressure over here. We can also use pressure We can also use pressure to determine the equilibrium constant. Why? Because pressure, it is proportional to concentration for gases in a closed system, which is true. Say, for example, you have a container over here, and this container has compressor in it, and therefore we have the gaseous molecules in this container. Now, let's say in this container, we choose to compress, right? We choose to compress these gaseous molecules, and these gaseous molecules, they're gonna cluster at the base of the container. It is true the volume has decreased, but now have a look at this. These gaseous molecules are under high pressure, and these gaseous molecules, they are close to one another, meaning they are concentrated. So high pressure means high concentration. Okay, high pressure means high concentration, so they are proportional to one another, the pressure and the concentration. And then for chemical equilibrium, you will see we're also going to discuss the factors that affect chemical equilibrium, such as temperature, volume, and pressure. And I say temperature, right? And what is this thing? A concentration, okay? Not the catalyst, but you will see as time goes by. So we can also express our equilibrium expression in this way using pressure instead of concentrations like this. Okay, so we still use the products over the reactants, and these coefficients, they still apply over there, which is this is species C and its coefficient, species D and its coefficient, and these are what are the products. Don't forget that. And therefore these are our reactants, which is A and B, and therefore this EQ just simply shows its equilibrium. Okay, all right. Now let's have a look at these examples. Okay, for example, we have the chemical reaction, or we ask this chemical reaction, it is a reversible reaction, right? So 2NO reacts with H2O to form N2 and H2O. So if we want to write the, sorry about that, if we want to write the equilibrium expression for this chemical reaction, we're going to say Kc is equals to the following. Remember, Kc all the times, we use concentration of the products divided by the concentration of the reactants. Remember, this is just reminder on how to reconstruct your Kc expression. So number one, you check onto this equation, you check your states. That's very important. Gases, 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 gases. This is homogeneous equilibrium, right? We are safe to plug everything on our expression. And then number two, make sure that your chemical equation, it is always balanced. Okay, why? Because you're going to have to use your coefficients to reconstruct your equilibrium expression. So is this equation balanced? Let's check. We have two nitrogens, we have two nitrogen on the other side of the equation, two oxygens, 2 multiplied by 1 is 2, and then there we also have 2 multiplied by 1 is 2, and then hydrogens we have 4, 2 multiplied by 2 is 4, and this side 2 multiplied by 2 is 4. That means the equation, it is balanced. Therefore let us write the expression. This is how we write it: products over reactants. The product is N2 and H2O, N2 and H2O. The coefficients here is 1, we raise them as our exponents. There the coefficient is 2, we raise it as exponent. The same applies to the reactants. Our reactants is NOH2, NOH2. And therefore, we use the coefficient for NO is to the power of 2 from the coefficient, and H2 is to the power of 2 from the coefficient. And therefore, this is how we write the expression, the equilibrium expression for this chemical reaction. Same applies to this equation. We want to reconstruct the equilibrium expression for this reaction. Let us check the states. The state is we have a solid, we have gas, gas, gas. This, it is heterogeneous equilibrium. We're not going to include our solid over here. If it was aqueous, therefore we were going to include it. But for the fact that this is a solid, we don't include solid and liquid, okay, on our Kc expression all the times. So that means, but the first thing is you must make sure that the equation, it is balanced before you can even cancel it out, okay? So let us see whether this equation is balanced. We have carbon 1, we have carbon 1. Hydrogen, we have 2, we have 2. Oxygen, we have 1, we have 1. The equation is balanced. Therefore, we get rid of our solid. Therefore, our Kc is going to be, remember, products over reactants. Our product is carbon monoxide and hydrogen gas. Carbon monoxide and hydrogen gas. The coefficient is 1, 1. And therefore, our reactants, we do not include carbon because it is in solid state. We include hydrogen, water, which is in gaseous state. I think it's a mistake, okay? It's supposed to be H2O, okay? Include H2O over there. And then the coefficient is 1. That's it. Remember, we said that equilibrium expression can also be expressed in terms of pressure, not only in concentration. Here, this C denotes concentration, and then this P denotes pressure over here. So our equilibrium constant, say we are given equation like this, we still use the same thing, products over the reactants. Our products in this case is NH3. And again, pay attention to the notation. For concentration, we use the square brackets, but for pressure, we use P as pressure at equilibrium. Pressure at equilibrium, we use the round brackets, and then we raise to the power of 2 from the coefficients of the balanced chemical equation. This is also balanced. And again, check that whether your equation is hetero or homo. This is homo. We can include everything. Gas, gas, gas. And therefore, here we use the products, and then here we use the reactants, which is N2, H2. The coefficients are still there. For N2, it's 1. For H2, it's 3. Okay, that's how we do this. Now, let's have a look at the equilibrium constant. Again, some other facts based on the equilibrium constant. Remember, this reaction, it is a reversible reaction. So, what is the Kc value? Or when we use the chemical equilibrium constant, what is the equilibrium constant of this equation? We're going to use the concentration most definitely, meaning we are talking about the Kc. So it happens that the Kc of this expression is 0,212, right? This, it is the rule for forward reaction. But now let's say the very same reaction, now we want to consider the reverse reaction. Is the Kc value for the forward reaction the same as Kc value of the reverse reaction? No, it is not the same, even though it is the same equation, but the Kc, it is not the same. The forward reaction is 0,212, but the reverse reaction, it will be the reciprocal of the Kc value of the forward reaction all the times. Because when you rewrite this equation, by reversing this equation, you're going to write it in this way, right? Whereby the products now are going to act as the reactants, and the reactant is going to act as a product. This is the reverse reaction. Remember, now the product is this one. It is no longer this one. You see? So that means you have to swap the reactants and the products. So we are talking about the reciprocal over here. So this reciprocal will most definitely yield to something that we see over here. So the Kc value for forward reaction, it is not the same as the Kc value of the reverse reaction, but rather it is the reciprocal. Okay, so when you multiply by 2 over here, when you multiply the whole equation by 2, by a factor of 2, therefore that will also affect the what? Remember, these are coefficients. These are coefficients that will also affect the Kc value. This is not going to be the thing. So that will also affect the Kc value, whereby we're going to raise to the power of 4 and to the power of 2. There is nothing special about this, but it's what we know. Okay. And therefore, here let us talk about the multiple equilibria. Okay. So we are still going to talk about, say we have number of equations. Okay. In this case, we have only 2. We have this reaction and this reaction. Okay. And we want to add these 2 reactions together. It's simple. So when you want to add these 2 reactions together, you're going to say this side plus this side, NOBr plus Br2 plus Cl2. But now, since well, this is equation, this is more or less like algebra or mathematics. Okay, let me just erase over there. I think, let me just do this. This is mathematics. We can see that we have 2 equations, equation number 1 and equation number 2. If you want to add the 2 equations, this most definitely will cancel with that one, right? Because they are opposite sides of the reactions. And therefore this plus this will give us this. And this plus this will give us that. Now, remember, each and every reaction, it has its own equilibrium constant because these are the reversible reactions. It has its own equilibrium constant. Most definitely, you would expect to add, since well, you've added the reactions, you would expect to add these two over here, and it doesn't work like that. In KC, when you add the two equations, you multiply the what? You multiply the two KC constant, you multiply the two equilibrium constants. So this one is K3. So K3 will be 0, 1. But how did we get this K3 of this reaction? We multiply this by that. So you're going to say 0, 0.014 multiplied by 7.22, and then you get your new K3, which is K3 for this equation over here. This is multiple equilibria. And I hope that was clear.